Warm welcome to all of you, this distinguished audience, and thank you for attending this special symposium on advances in ocular anti-infective agents. Also, we thank you for your attendance in advance of El Curso Interamericano. This year's course is going to be bigger and better than ever, and we're glad you're going to be a part of it. My name is Terrence O'Brien. I'm a professor of ophthalmology here at Bascom Palmer, and I've had a long-standing interest in ocular infectious disease, so I'm particularly delighted that tonight we have this opportunity to share some of this important information on behalf of your patients who are threatened by ocular infectious disease. I'd like to add my thanks to Dr. Cal Roberts, a longtime friend and colleague, as well as Luis Fernandez and the entire Bausch & Lomb team for this first pre-Curso symposium, which I hope will become a tradition that we will continue every year in advance of El Curso on subjects of importance to all of us. I'd like to thank Victor Perez, as well as our Jefe, Eduardo Alfonso, who unfortunately couldn't be with us this evening, and our distinguished faculty from whom we've already heard for their very comprehensive talks, as well as all of you, our Latin and South American colleagues. Now, we have to be careful with our approach to killing bugs and how we rationally achieve this effect of killing bugs. And hopefully you could start the video, Rick, if you could, with sound.
Patient has a fractured fibula, given a mild sedative, so I could be able to go in tomorrow.
Daddy's gonna be so excited.
That killed him.
So don't judge too quickly, and don't rely on anything other than the highest scientific data upon which to make your selection of an antibiotic. So in our remaining moments before we have our collegial reception together here in our courtyard, I'm going to discuss some of the contemporary approaches to antibiotic selection. And you've already heard some excellent talks on how we utilize the microbiology laboratory and the principles of anti-infective selection, especially pharmacodynamics, to maximize the likelihood of success. So we'll very quickly review some of what you've heard as far as the principles of therapy in eye care, especially look at a new agent, and we thank Bausch & Lomb for partnering with us to bring a new potent agent to our armamentarium in this escalating battle against species. We'll look at the pharmacodynamic principles, including speed of kill, and hopefully come together on some mutual consensus as to how we can try to stay one step ahead of the bugs. As we heard from Dr. Millot, there's global concerns that we're approaching the nuclear winter in the war of infectious diseases, and that the bugs have won out over the drugs, that we have no remaining effective antibiotics to help us and help our patients who suffer from severe infections. I think it's important to know the enemy, and that implies identifying the enemy and those formidable foes that we face in ocular infectious diseases. And this means we need the microbiology lab to help us with the epidemiology patterns of ocular infectious diseases, not only locally within our own region, but globally throughout the world. For acute microbial conjunctivitis, of course, we're worried about multiple bacterial species, including gram-negative species such as Haemophilus and Pseudomonas, but also formidable gram-positive agents like Staphylococci and Streptococci. We worry about viruses like adenovirus and more seriously herpes simplex virus, and organisms that are sort of in between a bacteria and a virus, such as chlamydial species. We've seen for different clinical conditions, we worry about different pathogens as the most likely threats causing the infection. With endophthalmitis, our most feared ocular infection. We know from the endophthalmitis vitrectomy study that approximately 94% of cases are due to the gram-positive pathogens, and only 6% are due to gram-negatives. And this data correlated well with the data from the microbiology laboratory here at Bascom-Palmer, where coagulase-negative staph account for approximately 70% of cases, Staph aureus 12.7%, strep, enterococci, and gram-negatives far less frequent causes of endophthalmitis. In elective refractive surgery, an infection is even more of a disaster in some ways, and post-LASIK keratitis remains a concern, and we'll talk more about this in El Corso on Monday. But we have seen unusual pathogens like non-tuberculous mycobacterial species, but gram-positive species still predominate, and more recent data suggests that many of these gram-positive bacteria are methicillin-resistant gram-positive bacteria. The second principle after knowing the enemy is to show some respect. And these bacteria have evolved over centuries to be very clever pathogens, and we are significantly outnumbered, and these organisms have the ability to adapt quite readily and quickly avoid our every effort at eliminating them. And in some ways, they represent the ultimate opportunists and survivalists, a very formidable foe indeed. We've heard a lot about resistance, and the fluoroquinolones in particular have unfortunately demonstrated increasing levels of resistance around the world for various infections, including ocular infections. And that's namely because the bacteria are not a stationary target. They evolve, and they've evolved several clever mechanisms to become resistant to fluoroquinolones. One is the impermeability through the porins in the cell wall, so bacteria may not enter. Another is the active efflux pump that may be present, decreased cellular permeability. But the most important is a mutation to one or more of the enzymes that are involved in bacterial DNA replication, namely bacterial DNA gyrase or topoisomerase 4, which leads to a decreased affinity for the fluoroquinolone molecule to the receptor and a decreased avidity, conferring often high levels of resistance among these pathogens that have developed these mutations to the enzymes involved in their replication and survival. We've seen that it's important to know the agents that we have available and their likelihood of success in any given infection. And there's been the evolution of fluoroquinolones over time from principally gram-negative acting compounds to increasingly gram-positive agents, and now with our most advanced generation, an extremely potent group of compounds that have broad spectrum of activity, but again, where we're worried about the development of resistance. So before we adjourn for our reception, I'll share the bad news that there's no one single universally omnipotent ocular anti-infective agent that will cover the entire microbial world. And the sad news is that these bacteria will eventually become resistant to every new agent which we attempt to develop. So we as a collective group of ophthalmologists still need to think carefully for the selection of optimally effective anti-infective agents. And we need our friends like Bausch & Lomb and others in the ophthalmic industry to continue to aggressively pursue not only the discovery, but the development of newer ocular anti-infective agents, this at a time where the costs for such a task become extremely daunting. We need newer agents, as we heard, better gram-positive coverage, especially against Streptococcus species, efficacy against the resistant organisms like the Staphylococci. We need agents that penetrate better into the anterior chamber so we can have greater activity and we can eliminate pathogens that may gain entrance. We talk about the 4 killer bees for the ideal anti-infective agent. That would be an agent that has, if we can go back here, an agent that would have bactericidal activity, so rapid killing, an agent that would have a broad spectrum of activity, biocompatible, being gentle to the ocular surface where it's applied, and most importantly, bioavailable, implying that it is present in sufficiently high concentrations to be effective at the site of action. And we have a new designer smart bomb in this war against bacteria in this molecule, besifloxacin, which is a quinolone, but is actually a chlorofluoroquinolone, having this chlorine at the 8th position rather than the methoxy group that is present in gadifloxacin and moxifloxacin. It does have the cyclopropyl group similar to ciprofloxacin and other fluoroquinolones. And it has this large, bulky side chain substitution at the C7 position that adds some steric hindrance and can help reduce the development of resistance with this molecule. What's most exciting about this agent has not been used systemically in any other capacity. Bausch & Lomb has been the developer of this exclusively for ophthalmic infections, so therefore the selection pressure perhaps has been less with this molecule compared with other fluoroquinolones. It also is formulated at a high concentration. Recall that fluoroquinolones are concentration-dependent killers, and this has a high concentration of 6 milligrams per milliliter. It's formulated too with a smart delivery system, a mucoadhesive technology that's been used with other anti-infectives such as azithromycin and with other ocular drops. But this is really a drug delivery device. It has a polymer polycarbophyll that allows this drug to be well solubilized and to be delivered to the ocular surface with a matrix suspension that then stays present with a longer contact time and is redelivered to the ocular tissues, offering some advantages in pharmacokinetics, as we'll see. With the human tear concentrations after a single drop of besifloxacin, you can see very high levels that are achieved for many hours after the installation of a single drop, well above the minimal inhibitory concentration of the pathogens causing ocular surface diseases and other ocular infections. Besifloxacin has the clinical indication for a number of important ocular pathogens that you see listed here, including gram-positive species, and most recently the addition of an important gram-negative pathogen, Pseudomonas aeruginosa, that we fear. There has been a surveillance program in the United States. First, there was the Ocular Trust. Sorry, if we could go back. There was the Ocular Trust program that was tracking resistance across the United States. And now the ARMOR program, which is an antibiotic resistance monitoring in ocular microorganisms, standing for ARMOR. And this program is designed to try to, as Darlene indicated, look at the landscape of organisms causing ocular infection and to track trends in their susceptibility patterns with in vitro testing. Seem to have lost the ability to advance the slides. Rick, if you could advance to the next slide. There we go. So these surveillance programs are designed to help us evaluate trends that are happening in resistance. And there have been a number of such programs, many of them listed here in countries such as the United Kingdom and elsewhere. With ARMOR, the purpose is to monitor the susceptibility trends with ocular pathogens. And there have been, over the last several years, efforts to look in particular at organisms of interest to ophthalmologists: Staphylococcus aureus, coagulase negative staph, streptococcal species, and gram-negative pathogens, including Haemophilus influenza and Pseudomonas aeruginosa. And this has been at academic centers such as ours here at Bascom Palmer, where Darlene has participated in the ARMOR study. at major eye clinics throughout the United States and university and community hospitals to track the trends of susceptibility to the most commonly used ophthalmic anti-infective agents, including the fluoroquinolones. And here we can see 4 of the 5 pathogens that have been included in the ARMOR surveillance program, including the gram-positives as well as Pseudomonas aeruginosa. We can look at the 2010 ARMOR surveillance data assessing the activity of fluoroquinolones against methicillin-resistant staphylococci, both coagulase positive Staph aureus and coagulase negative staph, and you can see the correlation of methicillin resistance with ciprofloxacin resistance. For all Staph aureus, we can see here that vancomycin still remains among our top shelf antibiotics that have activity against all coagulase negative staph as well as coagulase positive staph. But notice that besifloxacin has an MIC90 that is similar to that of vancomycin, whereas earlier generation fluoroquinolones or earlier introduced fluoroquinolones such as ciprofloxacin, gadifloxacin, moxifloxacin have far higher minimal inhibitory concentrations, indicating lesser potency. So for both Staph aureus and coagulase negative staph, the 2010 data were encouraging. In 2011, the trends continued, although you can see the activities for methicillin-sensitive staph differ for that of the methicillin-resistant staph, both Staph aureus and coagulase negative staphylococci, yet besifloxacin still remains a more potent fluoroquinolone option compared to the 8-methoxyfluoroquinolones and earlier fluoroquinolone generations. There is a Latin American ARMOR surveillance program that has been introduced this year and will continue next year, again looking at common ocular pathogens at sites in Argentina, Brazil, and in Mexico City. And I think there's still some expansion of sites across Latin and South America that we can discuss further at the break. The highlights of ARMOR are that besifloxacin, at least being the newer chlorofluoroquinolone, has greater potency compared to the older generation fluoroquinolones. But that's just part of the story. Remember, this is in vitro surveillance, and as clinicians, we want to really know, well, how does the agent work in vivo when we're treating our individual patient with an ocular infection? So for that, we need to dynamically integrate the in vitro data with the pharmacokinetics, and that is the essence of pharmacodynamics. So we need to look at really how we are penetrating into ocular tissues and then look at the potency data. And you can see here, because of the SMART delivery system, which is the Durasite vehicle that is supplied with the besifloxacin, we achieve very high concentrations over an extended period of time with just a single drop that well exceeds the MICs, the MIC90s of the most common pathogens that cause conjunctivitis and other ocular infections. With twice a day, we see even higher levels that are achieved that, again, exceed the MIC90s. And you can see with 3 times a day, the levels are even higher, but still with the once and twice a day, we are still achieving levels that are well above the MIC90 breakpoints for these organisms. So when we look at the data, we have to think not only of minimal inhibitory concentration, but minimal bactericidal concentration. And ideally, we'd like to think of mutant prevention concentration. That is where there are no longer any survivors, the concentration that kills all of the bacteria with 100% eradicated. And that typically is 8 to 10 times the minimal inhibitory concentration. So we are really at the top of the mountain with MPC, and there are death of all cells, no survivors, no mutations. no resistance. What we want to be careful of is achieving levels that are just at or around the MIC and dipping below the MIC, because that's the laboratory model for generating resistant strains of these ocular pathogens. In the development of besifloxacin, it was encouraging in non-clinical studies to observe lower frequencies of resistant variants that were observed in studies of the representative ocular pathogens. And you can see for Staph aureus and Streptococcus pneumonia, the rates of mutation were far lower for besifloxacin compared to either Cipro or moxifloxacin. And this is in part due to the dual targeting of both enzymes, bacterial DNA gyrase and topoisomerase 4, that besifloxacin demonstrates. And ratios that approach 1 represent more balanced dual targeting of the two important enzymes. And we can see for Streptococcus pneumonia and even a gram-negative pathogen, E. coli, that the ratio for besifloxacin is closer to 1 for both the gram-positive and gram-negative pathogen, indicating more balanced targeting of the two critical enzymes that are involved in the bacterial DNA replication. And why is this important? Well, the effect of mutations on minimal inhibitory concentration was shown in the last slide, which has flown by. And we can see that if we have only targeting one enzyme or the other, there's more likelihood for the development of resistance. And if we have balanced dual targeting, fewer survivors, fewer organisms that may become resistant, and a better situation. Next slide. Looking at the ocular pharmacokinetics further, we want to look not just at the peak concentrations, but really the area under the inhibitory curve. So again, not just the maximum concentration in the tissue, but the area under the curve that remains above the minimal inhibitory concentration. We recognize the difference between time-dependent and concentration-dependent killers like the fluoroquinolones. And if we can have a higher concentration for a longer period of time, we're more likely to be successful in eliminating a pathogen, whether it be on the ocular surface. And here we can see the very high levels of besifloxacin that are achieved in the tear film relative to gadifloxacin or moxifloxacin, and the area under the curve as is shown here. If we look and compare moxi and gadi with besifloxacin, we can see much higher area under the curve, under the inhibitory curve for besifloxacin compared to the other two advanced generation fluoroquinolones. What about the conjunctiva when you're treating conjunctivitis? Well, once again, due to the smart vehicle delivery, you see very high concentrations of besifloxacin that exceed those achieved for either gadifloxacin or moxifloxacin. And when we dynamically integrate these achievable tissue concentrations with the potency of the MIC value, which is lower for besifloxacin than either that achieved with gadifloxacin or moxifloxacin, we see that we have a superior area under the inhibitory curve for besifloxacin compared to moxi or gadifloxacin for ciprofloxacin-resistant MRSA as reported in the Journal of Ocular Pharmacology and Therapeutics, as shown here. What about the cornea? Well, we need a lipophilic agent typically to penetrate across the cornea epithelial barrier. And indeed, moxifloxacin has been shown to have some unique properties that allow it to achieve slightly higher levels in the cornea than either gadifloxacin or besifloxacin. But if we look at the potency again and integrate the potency into the equation, we can see once again that besifloxacin has a better ratio than either moxifloxacin or gadifloxacin because of the lower MIC, even with slightly less drug concentration in the corneal stroma, besifloxacin is more likely to be successful against these corneal pathogens. Well, what about aqueous humor? Well, we've known that moxifloxacin, again, tends to penetrate slightly better into the aqueous humor than either gadifloxacin or besifloxacin, but none of these fluoroquinolones, frankly, achieve levels in the aqueous humor that are likely to be protective in the case of a serious endophthalmitis with topical dosing alone. Nevertheless, again, if we incorporate the potency into the equation, as the late Harold New and his fellow Elner did with the inhibitory quotient defined as penetration over potency, we can see that we are more likely to be successful with besifloxacin than either gadifloxacin or moxifloxacin. Donnenfeld and colleagues have recently published in the Journal of Cataract and Refractive Surgery the human aqueous humor concentrations comparing besifloxacin to moxifloxacin and gadifloxacin with topical ocular application. And again, you can see that with all of these fluoroquinolones, the amount of achievable drug in the aqueous humor is frankly low, lower than what we would feel comfortable as treating clinicians with achievable levels that are likely to be successful for these pathogens. Nevertheless, again, if we combine the potency data and with the pharmacokinetics for methicillin-resistant, fluoroquinolone-resistant staph, besifloxacin has a higher ratio than either moxifloxacin or gadifloxacin for these species. And again, another way of graphically looking at the aqueous humor concentrations for both methicillin-resistant, fluoroquinolone-resistant staph epidermidis and staph aureus. Here we can see where we would have concerns that none of these agents with topical dosing alone are likely to provide the protection. Well, what about speed? Speed kills on the highways and byways, and it can also be beneficial when using an agent therapeutically as well as prophylactically. And the role of the preservative agent benzalkonium chloride has been studied in other fluoroquinolones, showing some superior rate of killing with benzalkonium chloride versus non-benzalkonium chloride. So the common preservatives that we use are helpful not only to protect the solution, but to enhance the kill rates, although in the tear film, the benzalkonium chloride is cleared very rapidly. So a more clinically relevant measure of speed has been conducted and recently published in the Journal of Antimicrobial and Chemotherapy as referenced here. And we can see that in these studies, besifloxacin was shown to have a faster kill curve, that is a steeper negative slope compared to either gadifloxacin or moxifloxacin. And notice that benzalkonium chloride at very small concentrations, 50 parts per million, has the fastest killing effect, but again is eliminated very quickly from the tear film. So what do we take home here tonight from this pre-Curso symposium that would help us choose the optimal antibiotic in clinical practice? Well, potency matters. The lower the MIC, the more potent the antibiotic is in vitro, and that generally translates into the in vivo situation, though not always. The inhibitory quotient makes good sense. The higher the IQ, the better. That goes for our children and grandchildren, as well as for the antibiotics, where a higher inhibitory quotient, that means there is more likelihood of success at a certain site, including ocular tissues, whether it be the preocular tear film, the conjunctiva, the cornea, and less so the aqueous and vitreous humor. Speed of kill is important. The higher the speed of kill, the faster the cidal mechanism of action, and we prefer cidal versus static antibiotics in clinical practice. seem to be going backwards. Can we go forward, Rick, here? Can we go forward 5, please? Okay, thank you. So in conclusion, for antibiotic selection, I think it's important that we know the enemy and the agents that we have available to help treat and protect our patients from serious infections. We need to be aware of the prevailing susceptibility data that is present not only in your own community, but the patterns of resistance nationally, internationally, and globally. Integrate pharmacokinetics with microbiological activity. Beware of just looking at MIC alone or concentration alone. We have to put these together in a rational way to have clinical meaning. And finally, analyze data very carefully and objectively, in vitro versus in vivo, and most importantly, randomized controlled clinical trials for our highest level of scientific evidence. And I want to thank, again, our kind sponsors, Bausch & Lomb, for helping bring besifloxacin to us as the only chlorofluoroquinolone that's available, that's not been used outside of ophthalmology. It's exclusive to our field and really has the greatest potency, a smart vehicle to deliver in high concentrations, and a fast speed of kill. Muchas gracias. Muito obrigado.